Okay, so what's a second reason for this decline effect, for the truth wearing off? Well, another one is just people make mistakes, and in some cases there's instances of fraud. And so there's some evidence here that these kinds of things are going up as well, as measured. One way to measure this is by the number of paper retractions, and the number of retractions has gone up fairly significantly, as Norden pointed out in 2011 in an article in Nature. So from the period of time 2001 to 2011, there's been a 10-fold increase in number of paper retractions, but only a 1.44-fold increase in papers themselves. Okay, and so this plot is from two different repositories, PubMed and Web of Science, neither one of which can include computer science papers, by the way. But you can see that it's gone up pretty significantly. Fine. So I'm not going to dive into too much detail into this phenomenon, but I do want to give you one statistical tool that is sometimes used to detect fraud, and that's Benfords Law. Okay. So if you're not familiar with Benfords Law, it's a fun one to be familiar with. So this law predicts the distribution of the first digit of data. Okay. And if you think about it without thinking too deeply, you might intuitively think that this would be fairly uniform. If you have random data, you might see an equal number of 8s and an equal number of 3s, an equal number of 2s, and so on. But it turns out that the distribution is not random in some circumstances, in many circumstances. Well, it's not even, I should say. It is random. It's just not even. The distribution looks more like this. You will get more 1s in the first position than you will 2s, and more 2s than 3s, and so on. And so up to 30% of the numbers you measure are 1s. So this should, blow your mind a little bit. Okay. So some examples of this, before we explain what's going on, taken from, there's a nice website, testingbenfordslaw.com, where they pull real data in and show the plots. This is the number of Twitter users by the number of followers they have. Sorry, not the number of Twitter users. Twitter users by the number of followers they have. Okay. All right, so the list of numbers is just the number of followers. The number of Twitter users that have, whose number of followers begins with the digit 1 is 32.62%, if you can see that. And the red dot is the prediction made by Benford's Law. So not too bad. The number of instances that have the 2 as leading digit is 16.66%, and there's the red dot predicted by Benford's Law, and so on. So not too bad. The distance of stars from Earth in light years follows a similar pattern. This is remarkably close to Benford's Law prediction. Government spending in the UK between the period of time May through September 2010. Again, remarkable prediction. Now, you might imagine there's some selection bias on this particular website, and I can't guarantee that there's not. But, with some reading plus a little bit of trust that I hopefully have built up, I hope to convince you that this is not fully explainable by this website choosing particular data sets for which this is true. Okay. Google books the number of unique 1 grams, and we talked about 1 grams a couple of weeks ago. Terms, essentially, are what 1 grams are. Okay, again, pretty good prediction. So before we give the intuition for this, the intuition is a little bit tricky, but before we attempt to give the intuition for this, you can use it to detect fraud. And so this was an experiment was done by Diekman in 2007 to see if this could be used for detecting scientific fraud. And so what he found was that first and second digits of published statistical estimates were approximately Benford distributed in real studies. Okay, or at the very least, they had kind of a monotonically decreasing distribution. So more 1s than 2s, and more 2s and 3s, and so on, if not exactly Benford's Law. And then what he did was ask subjects to manufacture regression coefficients, basically fitting a line manually, and found that the first digits were actually hard to detect as anomalous, but that the second and third digits deviated from expected distributions. And so this distribution that I gave you in the last few slides, and that I gave you in the actually, I guess I didn't give you the actual formula here. Okay, so the distribution that we'll be discussing is only for the first digit, and the skew in that distribution actually gets suppressed as you go to the second and third digits. But Benford's law can also be used to express different, yet still measurable distributions of second and third digits. And so there, the second and third digits deviated significantly. And so the conclusion was it is potentially useful as a fraud detection tool in scientific data. And there are instances where Benford's law has been admissible as evidence in court in cases of fraud, and it's been used by reporters and so forth to argue for evidence of fraud in cases of voting, election, and other kinds of accounting data on the sort of global scene. Okay, so what's going on here? Well, one way to think about the intuition here is imagine a sequence of cards labeled with a particular number, 1, 2, 3, 4, 5, all the way up to 999,999. Okay, and so put them one by one in a hat in order. And every time you throw a card in, measure the probability that a random selection from the hat would produce a card where the first digit is 1. Sorry, this isn't very well said. It's not drawing the number 1. Drawing a card where the first digit is 1. Okay. So what does that probability look like? Well, this figure's a little bit misleading because the x-axis is on the log scale. But if you just look at the heights, what's going on here is on the y-axis is the probability of drawing a particular digit. The blue line is associated with the digit 1. The green line is a digit 2, and so on. And this was generated by a simulation where I really did select random numbers from a distribution. And then I really did order them in the manner described in the previous slide, and put one in and then measure the probability of drawing it, a value with a number 1, or where the first digit is 1. Okay. And so if you think about this, the numbers, what's happened here, this is where 1, and this is 10, and this is 100, and so on. Well, as soon as I put a 1 in, the chance of drawing a card with a 1 in the front is 100%. When I put a 2 in, it's now 50%. When I put a 3 in, it's now 33%, and so on. But then as soon as I get to 10, it goes back up to a higher percentage again. And it stays there, 10, 11, 12, 13, 14, so on. And then as soon as I get to 20, it drops down a little bit. And so that's why it's climbing here, is through the 10s, and then it starts dropping again, sharply. Okay, and so the point here is that under this model, values where the first digit is 1 always are in the hat already by the time you get to the 2s. And the 2s are always there before you get to the 3s, and the 3s are always there before you get to the 4s, and so on. And so you end up with these peaks are led by the 1s, and the area under this curve, although remember this is a log plot, so the area is not quite right, represents the probability of drawing this. And so the probability does actually get higher. Okay. And there's a few different other models you can find if you read up on this, and I encourage you to. There's other ways to sort of think about the probability here, and there is actually a closed form expression for Benford's law as well. Okay. What are the limitations here? It's not always true, and one of the key situation in which it's applicable is the data set has to span many orders of magnitude. Right? It can't be values between, think about it. If you have values between 50 and 90 and you select those randomly, well, you're not going to get any numbers with the first digit is 1. Okay, and similarly, if you do from 1 to 100, well, you have this effect a little bit, but not universally. So you want to span a lot of orders of magnitude. And so this is sort of illustrated by this plot here, is that the red areas are represent the probability of selecting something where the first digit is 1, and the blue areas are where the first digit is 8. Okay, and so as long as you span enough orders of magnitude, you get much more area where the first digit is 1. Okay. But if you take a narrow case, well, and then the probability is more defined by the distribution itself, and there's not enough chance for this area under the curve under the digits 1 to get big. Okay. So fine. So I just want to introduce you to that law, mention that it can be used to detect fraud, and then connect the fraud plus chance of mistakes back to this original context we're in of trying to understand the weakness of statistical results, the perceived increasing weakness of statistical results.